Section 11.8. Our objective today is I can use lengths and areas to solve problems involving geometric probability. So remember that probability is the chance or likelihood an event will occur. And note, if the probability is near 1, it means that the event is very likely to happen. If the probability is near 0, then the event is very unlikely. In other words, it most likely will not happen. Okay, and we're going to use two principles today. So principle 1, okay, has to do with lengths. Okay, and so it says this: suppose a point P of segment XY, in other words, it's a point on the segment as XY, is picked at random. Then the probability that P is on segment XQ is equal to, it's a ratio. And so let me draw a picture here. So here's our segment XY, and we have some segment XQ, okay? And so the probability that P is in XQ is a ratio. It's a ratio of the length of XQ to the length of the whole XY. Okay? So it's, I always say it's like what we want is on top and the total possible is on bottom. Okay? So here's an example of how we would use that. So a friend promises to call you at home sometime between 5 p.m. and 8 p.m. At 5:30, you must leave unexpectedly for 45 minutes. What is the probability you miss the call? Okay, so what we need to do is set up a timeline. Okay, so their time begins at 5 p.m. and so here's 6 p.m., 7 p.m., and 8 p.m. So there's my timeline, okay? And at 5:30, which will be right here, this represents 5:30, you have to go out for 45 minutes. So you are gone this space of time. Okay, because this is at 6:15 here. Okay, so the time period, the probability that you miss the call is, this is 45 minutes is 3/4 of an hour, and the time, the total time where the friend might call is 3 hours. Okay, so if we simplify that, we get 3/4 times 1 over 3, or 1/4. So there's a 1 out of 4 probability that you will miss the call. Okay? Another example, similar example. Example 2. Every 20 minutes, a bus pulls up outside a department store. It waits 5 minutes while people get off and on the bus. Then the bus leaves. What is the probability the bus will be there when you leave the store at a random time? Okay, so here's the situation. Time starts here, so this is 0 and 20. So our time period is 20. And so the bus is actually at the stop for 5 minutes. Okay, so we want to know the probability that the bus will be here when you get out of the store. So probability is you want it to be there during that specific 5 minutes, but the total time period before another bus gets there is 20. So 1 out of 4. So again, the probability that the bus will be there when you walk out of the store is 12 out of 4. Okay, so that's using linear. Okay, so our second principle uses areas of regions. Okay, so the principle says, suppose a point P of region A is picked at random. Okay, so we have some region A, and inside A we have some region B. Okay, so that's the picture that we're looking at. Then the probability that P is in region B equals area of region B over area of region A. So A is the whole area we're considering, and B is what we want. So the area of what we want over the area that we are considering. Okay, so for instance, example. A dart lands at random at a random point on a square dartboard. Right, so question A, what is the probability that the dart lands within the large circle? Okay, so first of all, we need the area of the whole square. So area of square is 25 squared, or 625. Then we need the area of the circle, which is, the large circle has a radius of 10, so it's 10 squared times pi. And we're going to use 3.14 for pi, so we get 100 times 3.14 is 314. So probability in large circle is going to be the area of the large circle divided by the total possible area, which is the square. And if we express that as a decimal, we get 0.5024, I believe. So that's approximately 0.5. So you have to basically a 50-50 chance of getting in the large circle. So B, what is the probability that the dart lands within the small circle? Well, we're still using the same dartboard, so the total possible area is 625 units squared. Okay, so area of square is still 625 units squared. Okay, so then we need the area of the small circle. Okay, and so that the radius of the small circle is 5, so that's 5 squared times pi, or 25 times pi. And again, let's use 3.14 for pi, and so we get 78.5. So our probability in small circle is going to be 78.5, because that's where I want it, over the total possible. Okay, and again, if we change that to a decimal, we get 0.1256, so that's approximately 0.13, or a 13% chance of landing in the small circle.